Hello and welcome to the STM32U5 on Azure IoT Hands-On Lab. I'm Vanessa Villa, a program manager at Microsoft Azure.
I'm Alner O'Brien, a field applications engineer with STMicroelectronics.
And today, we're going to be connecting the Azure IoT Central application up to the B-U5 board Discovery Kit for IoT Node in a bidirectional communication pattern. So we'll be able to connect up the board and send data from the board up to the Azure IoT Central application, as well as send commands from the Azure IoT application down to the board. The power of the cloud and IoT is a progressive story. First, you start moving all of your operations up into the cloud. So this could be your day-to-day operations. This allows you to be globally available and have unlimited resources, really, when you are dealing with your day-to-day applications. Next, you want to start harnessing your real-world signals by leveraging sensors and devices and manage that centrally in the cloud as well. So by connecting up your day-to-day operations with these IoT devices, you can have further insight into what is going on in your end-to-end solution. The next progression in your cloud solution story would be edge and AI. Here, you can really leverage the power of distributed computing and intelligence on the edge by offloading some of that compute onto the edge and then further leveraging AI to drive insights from all of that data. The last step that your IoT solution progression usually takes is by leveraging digital twins. This is a full replication of your operations in the cloud in order to further harness insights and view opportunities to pare down and find additional information about your system operations. All of this is made possible by the Azure IoT product portfolio. It goes from prioritizing all of the different IoT verticals, such as manufacturing, buildings, which are known as spaces, retail, oil and gas, and agriculture. And we break it down into multiple level solutions and opportunities in order for you to pick and choose what would work best for you. For example, if you're just starting off with IoT, maybe a fully managed IoT solution would work best for you. As you start to discover your different needs, you might need to leverage other Azure IoT services or just in general Azure services in order to really refine your end IoT solution. So, for example, Azure IoT Central is built on top of Azure IoT Hub, Azure Maps. It has connection points out to Power BI and leverages Azure Active Directory as well. You could build your own custom solution and then further leverage Azure AI, Azure ML, and Azure Stream Analytics if you so desired. And so the real power of the Azure IoT product portfolio is for you to pick and choose what works best for your entire solution. A common architecture for an IoT solution would rely upon IoT devices, gateway devices, and IoT edge devices. So an IoT device simply would be sending up their telemetry signals. A gateway device would be connected up with perhaps shorter range devices or things that are not Wi-Fi enabled but could be Bluetooth enabled. And then the edge devices think of those as the outskirts of your operations and may have compute on them themselves in order to aggregate computer vision models or other such telemetry. All of that data then gets sent up to the cloud. It could be IoT Central, it could be IoT Hub, it could be some other form of route or endpoint there in order to aggregate all of that data. Once it's in the cloud, though, you have further extensibility points in order to harness the full power of the Azure cloud there, using Power BI or Power Apps and other web and mobile apps there. I think a key point here, though, would definitely be the interchangeability of several of the Azure offerings in order to fully refine your solution. And with that, I will throw back to Alner here from ST in order to fully discuss the STM32U5 IoT Kit. Alner?
Thanks, Vanessa. We'll dive right into our IoT Discovery Kit here. This is the kit we'll be using for today's virtual workshop. It's our STM32U5 IoT Discovery Kit. It's a purpose-built development board for IoT applications. It has a wide array of connectivity, including the onboard MX chip Wi-Fi module. It can also be expanded with a BG96 cellular module via the STMod Plus connector, the ultra-low power STM32U5 microcontroller, further means of connectivity with the STM32WB BLE module, convenient programming and debug with the onboard ST-Link virtual COM port, and then extensible connectors such as the Arduino shield on the back, a PMod connector, and an STMod Plus connector, the ST-Safe secure element on board, and then a wide array of sensors, including an accelerometer, magnetometer, pressure sensor, humidity sensor, time of flight sensor, and temperature sensor. The STM32U5 is a cutting-edge MCU with a ST-specific state-of-the-art security feature set, certified by both PSA, ARM security standard, and CESIP, an IoT industry security standard at level 3. It also comes best in class for power consumption with a 58 ULP mark. And it offers a rich application set with features such as SPI, I2C, USART, USB, a TFT LCD controller, a camera interface, extended memory interface, DACs, ADCs, op-amps, and comparators. There's also multiple advanced timers on board. The STM32U5 has heightened security, and it's based on ARM's Cortex-M33 with Trust Zone. Trust Zone is ARM's secure partitioning scheme. It allows for hardware-enforced boundaries between your secure and non-secure application. It also has built-in cryptographic acceleration for AES, ECC, and hashing, and it has a hardware-unique key for data protection. It also has hardware tamper detection and monitoring. The security set of the U5 pairs really well with the onboard ST-Safe A110 secure element. It has a pairing key for full-burst encryption to protect data physically on the device. It has cryptographic acceleration and handling and hardware to protect your private keys, and on-chip protected memory so your data never actually leaves the secure element. Most importantly, it has a factory-installed X509 device certificate, which DPS can use to uniquely identify your board in Azure IoT. Xcube Azure's TFM-enabled solution leverages the secure technologies provided by both STM32U5 and the ST-Safe A110 secure element. Trust Zone by itself is just a partitioning scheme, so you need a way to better utilize those services effectively. TFM is a reference implementation of ARM's PSA APIs and essentially provides a secure kernel for microcontrollers. It enables services like cryptography, root of trust, protected storage, secure firmware update, and secure boot. The TFM implementation provided in Xcube Azure integrates the ST-Safe hardware secure element to ensure a true hardware root of trust. The Xcube Azure application includes Azure RTOS, which is a complete microcontroller stack with a real-time operating system called ThreadX, which has a TCP IP stack called NetX Duo, and running on top of NetX Duo is a secure TLS library, and then there's also a cryptography library that provides an abstraction layer that enables us to integrate with TFM and ST-Safe to enable that true hardware root of trust. On top of TLS is the NetX Duo MQTT and embedded C IoT SDKs from Microsoft that enable the board to connect to Azure services like IoT endpoints and Azure Device Update and Azure Defender. These cloud services are tools like Azure IoT Central, which is a ready-made UX and API surface for connecting and managing devices at scale. Azure IoT Hub, a cloud platform that lets us easily connect, monitor, provision, and configure IoT devices. The Discovery Kit is actually already modeled in IoT Plug and Play, which means it's recognized right when it connects. And Device Update for IoT Hub is an offering where you can update your Discovery Kit with over-the-air updates for IoT Hub connected devices. Microsoft Defender for IoT is a service that provides unified threat protection for all of your IoT devices in the field. The Xcube Azure solution is a complex one. And to minimize the out-of-box experience and time to market, as well as time to getting your board delivering telemetry data to the cloud, we created this Quick Connect, which is essentially a Python script that minimizes all of the out-of-box experience into a short scripted process. It's great for proof of concepts, cloud engineers, and solution builders who want to deal with building applications and not fret over building firmware images, managing the cloud, provisioning devices, and copy-pasting certificates from serial prompts. So how the Quick Connect flow works is essentially a user would run the Quick Connect. It would manage some of the installs for Azure CLI on board your PC, log you into Azure CLI, create some Azure resource for you in the cloud, then move over to the device side, set some option bytes for the board on the device, flash the firmware image that's pre-built in Xcube Azure, and then find the COM port for the board so it can communicate things like your Wi-Fi credentials, and then also collect the cert stored on the secure element and the common name embedded in that cert in order to create a device in your IoT Central app and an attestation with that X509 cert for that device. All of the credentials written to the device will be stored in TFM secure storage, and once the device is reset, it will boot back up and connect to your device in the cloud and begin publishing telemetry data. With all that information, we'll be running the Quick Connect in our virtual workshop. First step is to connect the micro USB cable to the port closest to the MX chip Wi-Fi module on board. The MX chip Wi-Fi module on board the U5 Discovery Kit requires a 2.4 gigahertz Wi-Fi network. If you're unsure about the configuration for your Wi-Fi network, you can navigate into Search, and we will start a mobile hotspot on your PC. You can search for hotspot. We'll turn the hotspot on, and then we'll make sure that power saving mode is disabled. We'll click Edit, create an SSID and password that you are familiar with, and then when you choose network band, ensure that you click 2.4 gigahertz. Save these configurations, close the window, and now you have a guaranteed 2.4 gigahertz Wi-Fi network for your board to connect to. To continue with the virtual workshop, you should have completed the prereq check prior to this video. A link will be provided in the description for your review. Now, we can navigate to our C drive, and we'll see Xcube Azure extracted here. This was done for you with our prereq check script. Next, we'll navigate into Projects, and then B-U5, and Applications. Here we have two application folders. TFM Azure IoT is the reference design with TFM enabled, trust zone enabled, and ST-safe utilization. NetX Duo is more for proof of concepts. It doesn't include the heightened security levels. Today we'll be using TFM Azure IoT, so we'll navigate into here, and then go to Azure Scripts. This is the home for our entire Quick Connect flow. The Quick Connect Python script is here. To run the script, we'll navigate into the address bar and type PowerShell. This will open a PowerShell directory, or a PowerShell in this working directory. And then we'll type Python, st, tab to complete, STM32U5 Azure Quick Connect.py, and we'll want to run the script in interactive mode. So we'll append the -i argument. Okay, so the script will prompt us to answer yes or no for whether or not we have an active Azure subscription. An Azure subscription is required for today. So we'll enter Y. Next, we'll be prompted with different configurations for how we want the cloud to be configured, one of which is the app name. You'll want to choose something unique that doesn't include any special characters, only alphanumeric characters and dashes. So for today, we'll choose VWS for Virtual Workshop 1254. The SSID is the one we set up on our hotspot. So STIoT demo. And our password. And then the resource group is one that you can create. So choose something, again, unique, or if you have a resource group you've already created, you can enter that name here. And for location, I'll be using the West US servers. Next, the script will log us into Azure CLI. This is the account we'll be using today. And from this point forward, the script will run completely autonomously. It will create that resource group that we named earlier. Next, it will create a central app with the name we entered above. This execution may take some time, so feel free to pause the video and restart it whenever your execution is complete. Now we'll hand it over to Vanessa to explore the Azure IoT Central dashboard.
Thank you, Alner. So today we're going to explore the IoT dashboard. And first off, we're going to see this raw data. Here you can explore all of the different message types and see exactly what the data your device is sending. But let's check out the dashboard. So the dashboard takes that data and plots it on graphs or gives you certain aggregations over time periods. For today's exercise, we're going to add an additional tile on this dashboard to show a raw telemetry. As you can see on this graph, you do have the temperature here, but it gets averaged out on this particular graph. In order to edit this device dashboard, we're going to head over to device templates. Here on device templates, we can see our device model. And from here, it'll show you all of the components and all of the capabilities and telemetry that this device sends. Over on the views section, this is where we will be able to edit our dashboard. In the Overview tab of Views, here we can see the device dashboard that we just saw. We're going to add a line chart and now configure it by clicking on this pencil icon. Here we will change the title to Temperature Last 100. On the display range, we will select the last 100 values. Here under the telemetry section, we will click plus capability and select the temperature capability. We now hit Update, and this tile is configured. We click Save in order to save this dashboard. Saving this dashboard saves the work but does not push it out to your existing devices. In order to do that, we have to click Back and Publish. This notification window tells you that your device template has been updated, and in particular, the views have been updated. We now click Publish to push this out to your existing devices. Now that your device template has been published, let's go back and check on the device. As you can see, this tile now gives us the last raw 100 values for temperature. In order to further dig into our device's telemetry, we can go to the Data Explorer. Here, we will click plus New Query and be able to select the device group, which is the B-U585 device. Additionally, you will be able to select the telemetry on which you wish to query. So for today, we will select temperature, pressure, and relative humidity. You can group by things like device ID, device model, manufacturer, or other properties associated with the device. Because we have one device versus 100 or 1,000 devices, we do not necessarily need to group by anything today, but we will select device ID. Now we click Analyze. You can adjust the query time frame by clicking on the calendar and setting it to the last hour, to the last 2 hours, or be able to configure your own time range within the last 90 days here. For today's example, we will click on the last hour and click Save. Now we can start to see the device data that has been sent today during this workshop. In order to further query, we can zoom in and adjust the interval size. The interval size bucketizes the data according to average, min, max, count, and sum. All of those are configurable on the telemetry panel on the side. You can adjust the interval size from seconds all the way up to minutes in order to smooth out your data. You can post this query as a dashboard tile by scrolling up to the page and clicking Save. Naming the query, clicking the Save button, and then being able to select a dashboard to pin it to. This will save it to the top-level dashboard within your IoT Central application. If we head on over now to the Dashboards page, we should be able to see our query. We're going to configure a job in order to run a restart command down on the device. We go and click plus new, name the job, and select the device group on which this job should run on. This page will tell you how many devices this job is going to run on. Down in the Job Properties section, it will ask you for the job type. Here is where you select what you want to update or change. In this case, we want to run a command. The command will be the reset command. There's several ways to run a job. You can enable batches in order to run jobs across large numbers of devices and stagger out those job requirements. Additionally, you can enable the cancellation threshold so that if a certain number of the jobs fail or run with errors, you can prevent it from running the next batch. You can additionally schedule this job to run in the future. Today, we are going to enable that feature. Select a one-time recurrence and start it today within the next few minutes. You can review the configuration here and hit Schedule. The job is now scheduled, and if you go back to the Jobs page, you will be able to see it here. If we go down to the terminal, we will be able to see this job run. As you can see now in the terminal, the device is resetting and now rebooting. During the reboot, you can see the certificate as well as the registration ID for the device. Here in the terminal, you can also see that it has been connected to IoT Hub again and that the properties have been sent. The device is once again sending telemetry. Back in the IoT Central application, we'll be able to export out that data. We go down to Data Export and select Plus New Export. Here, we name the export and select the type of data we wish to export. For today's lab, we're going to select telemetry. You can add additional filters, such as device ID, device name, organizations, whether the device is simulated or real, or other custom properties if you so choose. You can also add enrichments if that's necessary for your line of business applications or for other extensibility purposes. This export needs a destination, so we will click Create a New One and name the destination. There are several different destination types that are supported, ranging from Azure Blob Storage, if you simply need to export your data for redundancy or as a backup, Azure Data Explorer, if you want a custom organized Azure database with several different extensibility points, different retention policies, and extensibility points, Azure Event Hubs, if this data needs to be routed to a different endpoint, Azure Service Bus Queue, if you need this data to be enqueued up for a specific endpoint, and Azure Service Bus Topic, if this needs to be routed to a certain topic that is going to be subscribed to by some other Azure service, as well as webhooks. For today's lab, we are going to select webhook. At this point, you'll notice that there is a callback URL as well as an option for authorization and headers. We need to generate the callback URL for our webhook endpoint. We will go up, select New tab, and enter webhook.site. This is a free site where you will be able to generate a webhook URL for at least 100 to 500 requests. Copy the unique URL to your clipboard and go back to your IoT Central application. paste the callback URL, and click Create. Additional data transformation is enabled if you choose to alter the schema, the JSON, or change the shape of your exported messages into a new format. Click Save. And notice that the Destinations section of this page has export status as starting. In order to further monitor this, we can head back to the top-level data export page and see that the export is also starting with a telemetry destination. Back on webhook site, we can see that the telemetry is starting to flow from the IoT Central application out to our webhook. You can see the entire raw data message from IoT Central, including information like application ID, device ID, telemetry, and template ID. We're now going to go back to the IoT Central application and disable this export. Thank you so much for joining this workshop for the IoT Central portion. If you feel like you would like to further investigate the Azure IoT product portfolio, you may do this entire workshop on IoT Hub as well. And back to Alner for resetting the device.
Next, we'll be building the firmware images that were precompiled in the Xcube Azure project. If you wanted to customize the firmware in any way, you would need to build the project, currently available on IAR, and in the near future will be available on Cube IDE for build. To build the project in IAR, we'll navigate back to our C drive. And to avoid any file path length restrictions, we'll open up PowerShell in this directory, and then run the command subst and choose a volume name that's not already being used. For my application today, I'll be choosing T, and then tab to complete STM Cube Expansion Cloud Azure v2.1.0. What this command will do will replace the long file path name with the volume letter T. When we close the PowerShell window, we'll see that we have a Windows T volume here. We'll navigate inside and go into Projects, B-U5, Applications, and TFM Azure IoT. To open the project in IAR, you can double-click the Azure RTOS project file. In the toolbar, select Project, Batch Build, and Make. There are 5 projects that will be built in order. These projects comprise the binary files that were flashed when we ran the tfm update.bat script. This will take some time, so feel free to pause the video and return once your build is successful. As you can see, we have a successful build. Now that we've built the project, you could flash any of the firmware images that you've modified with that tfm update.bat script. And depending on the changes you've made, it may or may not work with our quickconnect.python script. All right, there's one final step. Basically, we'll just want to clean up all the things that we've done during our virtual workshop today. First, we'll turn off the hotspot that we enabled. To do that, we'll go back to our hotspot settings and just make sure we turn this off. Next, we set some option bytes on the board to enable trust zone for this Xcube Azure project. To disable those, we'll go back to our C drive, Navigate into our project, B-U5, Applications, TFM Azure IoT, TFM SBSFU boot, eWarm, and we'll want to run STM32U5 trust zone disable. To run the script, you can double-click. It will prompt you with a PowerShell window where you'll have to say yes to acknowledge that you have a trust zone enabled project flashed to the board. We'll click Enter, and the script will reset the option bytes we set on the board. Now your board is back to factory settings, and your mobile hotspot is off. Everything is cleaned up. And that concludes the hands-on portion of our virtual workshop. Thanks for attending today. If you have any additional questions or any problems running the material, please feel free to contact us on links we'll provide at the end of the presentation.
Thank you, Alner. Today we're going to go over the resources where you can extend this workshop even further. The first one is aka.ms/stazure to find all of the links and all of the material from today's workshop, as well as additional support and extensibility points. If you would like to know more about the IoT Central and IoT product portfolio aspect of this, you can find Learn modules at MS Learn. If you would like to connect the STM32U5 to IoT Hub, you can find that article at communityst.com/s/article/Azure IoT Hub. Once you have your device connected up to IoT Hub, you can then leverage Azure Device Update at github.com/azure-rtos/samples, and soon the ADU support will also be available in Xcube Azure. Thank you so much for joining us for this workshop. Bye.
Bye-bye.